pleasure to have Leon Bungert as a speaker today. He's currently at the Hauser Center for Mathematics in Bonn. And he's really a great example for combining mathematical techniques in different areas, sitting at the intersection of PDE analysis and data science and data analysis, bridging imaging, calculus of variations, methods on graphs, and techniques of machine learning, really at the intersection of several different topics. And today, he'll be sharing with us on infinity Laplacian equations on graphs, which is, I'm very much looking forward to hear this, as it's recent work in the line of work that Leon has been working on P Laplacians and infinity Laplacians. So Leon, you have the floor.
Yeah, thank you very much, Franca, for the kind introduction. And of course, thanks to the organizers for inviting me to give a talk here in this nice seminar series. As Franca said, today I will speak about a topic which, if you just look at the title, doesn't sound like it has very much to do with machine learning. So the title is Uniform Convergence Rates for Infinity Laplacian Equations on Graphs. However, as I will convey sort of in the first part of the talk, graph PDEs have very strong connections to semi-supervised learning methods. And so the rigorous understanding of graph PDEs is also very helpful sort of for analyzing semi-supervised learning. So this talk is based on joint work together with Jeff Calder from the University of Minnesota and Tim Reuth from the University of Erlangen. And it's basically based on two papers, one of which is about a year old and was published recently, and the other one is brand new, so it only came out, I think, 10 days ago. Okay, and so let me also remark that sort of if there's any question during the talk, please feel free to ask directly. I don't want to lose anybody, so just type it in the chat. I'll try to monitor that, or just unmute yourself, whatever feels right for you. Good. With that being said, let's start with the talk. And I would first like to speak about graph-based learning and its connections, well, to machine learning. And then I will tell you a little bit about continuum limits of graph-based learning methods in general. And then a bit more specific, I will speak about our results for the infinity Laplacian equation on a graph. And as it will turn out, understanding the infinity Laplacian equation is, for this, it's sufficient to understand the distance function on a graph. And so in this fourth paragraph, I will speak quite a bit about how distance functions on a graph converge to a geodesic distance function in a continuum. And then I will present some numerics and an outlook. Okay, so let's get started with the intro in graph-based learning. And for this, let me first recap a few learning paradigms. So let's say we're given some data set omega n, which is just a collection of n points in some feature space Rd. And then there are different learning tasks that we could try to solve. The first one, and probably the oldest one, is the task of unsupervised learning. So there you just take the raw data as it is, illustrated by these points here, and you want to, let's say, cluster the data into the left part of the data belongs to the blue class and the right part belongs to the red class. And so there are different methods for achieving this task. There's the k-means algorithm, which is very traditional, but also expectation maximization works for that problem. And a bit more sophisticated, you can also use graph-based methods and do spectral clustering. Okay, so this is the world of unsupervised learning, and I'm not going to speak about that today. Then sort of on the opposite end of the scale, there's supervised learning. And here the situation is completely different, because in supervised learning, every data point carries a label. So for every point, you already know whether it belongs to the red class or to the blue class. And then the question is, what is the task? Well, the task is to extend this information to the whole data space, right? So you want to find a function that you can evaluate at any other point in space. And this function should coincide with these prescribed values quite a lot, I would say. And nowadays, sort of the most popular method to find such a function is to parameterize it with a neural network. And then you might get a result like that. So you get a function which classifies the whole space into red and blue. And to a very large extent, this function coincides with what you prescribed up here. So this is supervised learning. But of course, there's also something in the middle where you don't have full information about your data, but you also don't have no information. And so what's in the middle is called semi-supervised learning. So here, a few data points carry labels. For instance, you might know that this point is blue and the other point here is red. And you want to use this very sparse information to, to find the labels of the other points in your data set. And this occurs typically when getting data is cheap, but getting labeled data is expensive, right? And sort of a prototypical example for that is medical imaging, where you get CT scans and MR scans on a daily basis in a hospital, but sort of classifying all of these images requires a doctor, which is expensive. So that's when you can use semi-supervised learning. And so here the task is, as I said, to extend these labels to the rest of the data set. And there are also different methods to do that. So the easiest method would be a nearest neighbor approach, where you just look for the closest point that carries a label, and you assign this label to the unlabeled point. Or you could do something which is a bit more sophisticated and works much better, namely graph-based learning. And this is sort of what my talk focuses about today. So let's speak a bit about graph-based learning. So again, the situation here is as I just described. So we have some data set omega n, and we have some labels on a small subset of the data set, and I call this subset curly on, right? And so these labels I can represent with the function g, which is defined on that label set. And then the task is to find a, well, here I wrote smooth function, but we could also just say to find a nice function u, which is defined on the whole data set and which extends the labels. That means that on the small label set curly on, u coincides with the label function g. And of course, there are infinitely many choices of such a function u, and that's why I wrote here smooth, or you could also think about a nice, as I just said. So you somehow have to prescribe a bit more information to select a reasonable function here for this task. And sort of a way you can do that is you construct a specific model. And the model that people like to use in this field is the model of weighted graphs. So you don't just take the data as it is, but you use similarity of data points to construct a weighted graph structure on top of the data, right? So which looks like that. So you basically draw connections between points, between data points which are similar in some metric, and you use this additional information to set up a meaningful task. And so if you have such a graph structure with connections and with weights, then you can actually speak about smooth functions in a mathematically meaningful way. And you could try to find such a smooth function defined on that graph. And so that's basically the story of graph-based learning. So, and the literature in that field is vast. Graph-based learning has first been used for the task of unsupervised learning, namely for spectral clustering, as I mentioned in the beginning. And so there are a lot of results about Cheeger cuts on graphs and spectral clustering on graphs, and how this is consistent with, for instance, eigenvalue problems or Cheeger cuts in a continuous fashion as the number of graph vertices tends to infinity. Right, so this is sort of the world of clustering, but then there's also a huge body of literature on semi-supervised learning methods. And most of them actually involve some sort of Laplacian operator on the graph. So there's Laplacian learning, which was originally, well, invented, I should say, by this paper from 2003. And then it was sort of heavily improved upon later, and also extended to a nonlinear problem, which is called P-Laplacian learning. And furthermore, this was generalized, or a certain limit was taken in order to derive infinity Laplacian learning, which is what I will speak about today. And then there's also Poisson learning, where you solve some sort of Poisson equation on the graph. And there are millions of other methods. So in a nutshell, this field of graph-based learning, in particular using PDEs on graphs in order to solve semi-supervised learning tasks, is sort of very well understood and very popular these days. And let me just mention that also, besides these Laplacian type methods that I just reviewed, there are also other methods based on the MBO scheme, for instance, or based on the iconal equation, which is yet another PDE on a graph. Okay, so but let's go back sort of to this Laplacian world, and I would like to explain you a little bit more in detail what P-Laplacian learning is, because this will sort of lead us directly to what I will speak about today, namely the infinity Laplacian operator. Okay, so just remember what we want to do is we want to find a function on our graph which extends the labels in a smooth way. And so in P-Laplacian learning, you sort of incorporate this smoothness by solving a PDE on a graph, namely the P-Laplacian equation. So you have some differential operator here on a graph, which is a nonlinear operator, and you solve this kind of equation. So your function should be p-harmonic wherever there is no label, and on the label set, it should coincide with the label function. And equivalently, you can write this as a minimization problem. So where this energy that you're minimizing here is the P-Dirichlet energy, and its its derivative coincides with this operator. So let me tell you now what this operator looks like and what the energy looks like. Maybe let's start by looking at the energy down here. So here you can see that this energy really sort of penalizes non-smooth functions, namely in the following way. Whenever the function u is such that for 2 points which are very close together, that means they have a large weight, the values of the function u are sort of far apart from each other, then the value of this function is large, right? So minimizing this functional means that the function u that you get out of it sort of doesn't jump too quickly from one vertex to a nearby vertex, right? And as I said, the optimality condition for minimizing this problem is precisely this P-Laplacian equation, where this is the P-Laplacian operator on the graph. And for those who know the P-Laplacian sort of in a continuum setting, you can sort of see some similarity. This is some sort of discrete gradient raised to a certain power. And here you have the gradient again, and then you take a sum which sort of mimics the divergence. So this is the P-Laplacian operator on the graph. Okay, and so this problem has been very well understood in the last years, and in particular, it is known what happens if the number of vertices in the graph grows to infinity, which basically models that you get more and more data. And then you can sort of tackle this problem using Gamma-convergence, and the ingredients for that are the following. So you assume that the graph points, so the data points, are sampled from some distribution rho that you do not have to know a priori. It's just the data distribution of your data in the natural world, let's say. And then you need another ingredient for this Gamma-convergence result, namely you have to choose geometric weights. That means that the weights on your graph are small whenever the distance of the two data points is significantly smaller than some value of epsilon, and the weights are small whenever this distance is bigger than some value of epsilon. And this value of epsilon here it's a scaling parameter, and this turns out to be very critical. And you typically need that this epsilon is significantly bigger than the connectivity threshold on a random graph, which is this value here, where n is the number of points in the graph. And however, choosing a large epsilon is sort of undesirable in practice, because it means that your graph has a lot of edges, and then things become computationally inefficient. So what you want to do is you want to choose epsilon as small as possible, such that you still get a reasonable continuum limit if you have a lot of data points. And then let me also remark that sort of continuum limits for the P-Laplacian problem are only valid if the dimension of the data is smaller than the value of P. And that means that in a data science context, where the data dimension can be really large, you in principle have to choose a very large value of P here, which again makes the PDE that we saw on the previous slide relatively nonlinear. Whereas for P equal to 2, you have a linear problem. And okay, but under these mathematical assumptions, let's say it was proved by Slapchef and Thorpe that these Dirichlet energies that we saw on the previous slide, these discrete ones, they gamma converge in a certain sense to a continuum Dirichlet energy, which is now an integral, basically the p norm of the gradient. And you have this density popping up here. So this rho again was the density from which the points are sampled, right? Okay, but as I said, sort of the problem is that this is only true if p is bigger than the dimension, and this is not just a mathematical sophistication. It's something that really happens if you run the algorithm on some data. So many people in this field like to show this picture here, and what it shows is the following. So you just take a few data points here in the plane, so it's a two-dimensional setting, and you solve the Laplace equation on the graph. So p is equal to 2. With two labels, one red label here and one blue label down here. And you see that the solution that you get is completely useless because the solution is 0 everywhere apart from the two labels where it's -1 or +1. So you cannot use this solution that you get out of this PDE in order to say any meaningful thing about the other data points, right? And in particular, the smoothness that we were hoping for is not satisfied here. Right, and so the reason for this phenomenon is that 2 is not smaller than 2, which is the dimension. So if you want to use Laplacian learning or p-Laplacian learning, you really have to choose large values of p. And this somehow motivates to take p to infinity, because if p is equal to infinity, you've sort of covered all of the cases that you could ever encounter. And this then leads to the Laplace equation on the infinity Laplace equation on the graph. So, and this works as follows. You take the p-Laplacian equation, which we saw before on a graph, and then just formally you send p to infinity. And then what happens is the following. So you can split the sum into a positive part and a negative part, bring it to the other side and rearrange things. And then you will see that if you send p to infinity, you will get the following equation. And you don't have a sum over all data points anymore. But instead, you have a minimum over all data points and a maximum over all data points. And sort of the sum of this min and the max has to be 0. So this is the infinity Laplacian equation on a graph. And so what this models is some sort of discrete mean value property of solutions. So if you have a solution of this equation, then this means that if you average the max around a point and the min around a point, you get the value of the function at that point. So this is sort of some sort of discrete mean value property here. Okay, and it turns out that this using this graph infinity Laplacian equation so solves this spiking problem that we saw on the previous slide. But of course, it would also be useful to mathematically understand this equation in the continuum limit. So that means if you have infinitely many data points. And so let me first remark that there's also a variational problem associated with this graph infinity Laplacian equation. And to understand the variational problem, let us define the graph distance function. So the distance function on a graph between two vertices x and y is just the minimal value of this sum here, where you minimize over all paths in the graph which connect x and y, and you sort of sum up the reciprocal weights of these paths. And here you see that sort of if one of these weights is 0, then you get an infinity. So you cannot take a path which sort of jumps between two vertices which don't have a connection. So the weights have to be positive for this path to be admissible for this minimization problem. And then you get the graph distance function like this. And if you have a distance function, you can also define a Lipschitz constant, right? Because the distance function is a metric. And so you can define Lipschitz constants of functions on graphs. So here v is a function on a graph, and you define the Lipschitz constant to be this value here, where you just replace the usual Euclidean distance that you would have down here in the denominator by the graph distance. Okay, so the question is, why do you want to do that? And the reason is that this Lipschitz constant plays a very important role in the variational problem that accompanies the infinity Laplacian equation on the graph. Because it turns out that any solution to the infinity Laplace equation on the graph is a Lipschitz extension of the labels. So a Lipschitz extension means that on the label set u equals g, as we want, and outside the label set, u has the smallest Lipschitz constant possible. But not only this is true, but in fact, u is a Lipschitz extension on any subset of the domain. So whatever subset X you choose of your graph, u will be a Lipschitz extension even on that small subset. That means basically that u is also locally optimal in the sense of minimizing the Lipschitz constant. And this is referred to as absolutely minimal Lipschitz extensions, which is written here in the title. Okay, so this basically tells us that the variational problem associated to solutions of the graph infinity Laplace equation is the problem of absolutely minimizing Lipschitz extensions, which is a very desirable property because remember, we want to extend our labels in a smooth way. And if the function u is even Lipschitz continuous, then this is sort of the smoothest extension we could hope for. Good. So this is just an illustration of these absolutely minimal Lipschitz extensions. Let's say you prescribe the red points. So let's say these are your data points in 1D. And then there are several ways how you can extend these data points to the whole interval by maintaining the Lipschitz constant. And sort of the green solution is one possible solution. The purple solution is also a solution. But probably you would not argue with me that the blue solution is the thing that you might prefer. And the reason is that the blue solution is also locally a Lipschitz extension. So whenever you take a small subset here, u has the smallest, the blue solution has the smallest Lipschitz constant possible. And so in fact, it turns out that these Lipschitz extensions are also unique under certain circumstances, which is also a desirable property. Okay, and so now the question is, what could be the continuum problem of our graph equation? And it turns out that the continuum problem also has something to do with Lipschitz extensions. And for this, we basically make the same definitions as we just made on the graph. So first we define a distance, but now we're in a continuum domain. So we don't use a graph distance, but we use a geodesic distance, which is the length of the shortest curve connecting 2 points x and y. So if you're on a convex domain, then the length of the shortest curve is obviously equal to the Euclidean distance. But in a non-convex domain, this geodesic distance is in general larger than the Euclidean distance. And okay, having this geodesic distance at hand, you can also define Lipschitz constants like this. And okay, just a remark here, you can completely forget about the Euclidean setting kind of once you made these definitions here. You can just regard the domain that you have together with this geodesic distance as a length space. So it's a metric space in particular, and you can just use the topology of this length space. So you don't have to work with the Euclidean topology anymore. And then the continuum problem is the following. Namely, you take an arbitrary label set in your continuum domain, which is closed. It could be the boundary of the set, but it could also be a collection of points. It could be basically anything. And then the continuum problem is that you want to find a function which is a Lipschitz extension of the label function outside this label set curly O. And Lipschitz extension now means the same thing as we saw previously, namely that the Lipschitz constant of u is locally optimal for all subsets of the domain. So this is the continuum problem, and we will basically show that our graph problem converges to this problem, and we will even prove quantitative rates of convergence. But let me first make a very brief remark, namely, since we're solving a PDE on a graph, there should also be a PDE in the continuum, one might think. And indeed, this is the case. So if this label set coincides to the boundary of your domain, then being a Lipschitz extension in that sense is equivalent to solving a PDE, namely the infinity Laplacian equation, which is given down here, where the infinity Laplacian operator is defined like that. So this is quite an exotic differential operator, and it's pretty hard to understand, whereas these Lipschitz extensions are in fact much easier to understand. So don't worry too much about the PDE down here. Okay, So let's now speak about continuum limits of graph-based learning methods in a bit more general sense, before we then sort of specialize the discussion to the problem of the infinity Laplace equation. And in general, if you have a graph and a problem on that graph, and you want to understand how it converges to the continuum problem, there are two very important quantities involved. The first one is the graph resolution, which I abbreviate with delta n. And the graph resolution is defined as basically the Hausdorff distance between the graph and the continuum domain that you want to approximate. So the Hausdorff distance is defined down here. It looks a bit complicated, but it's very easy. Namely, the Hausdorff distance is sort of the maximal distance that could occur between a continuum point and the closest graph point, right? So this means that whenever this Hausdorff distance is small, you can always find a graph point which is very close to every continuum point, okay? And you also have to assume that the Hausdorff distance of the labeled set is close to the Hausdorff to the label set in the continuum. But anyhow, so this is the resolution of the graph, and you can compute this funny Hausdorff distance explicitly in a lot of settings. For instance, if the graph is just a regular grid in d dimensions, sorry, then the Hausdorff distance is 1 over n to the power of 1 over d. So it's a very easy computation. You just sort of paint points in a grid and sort of compute what is the maximal distance. If the graph is not a regular grid, but an IID sample from some positive distribution, then this Hausdorff distance is almost the same expression, but you have a log factor here. So it's a little bit bigger, and this log factor comes from the stochasticity of sampling. And this is true almost surely. And okay, so this is the resolution of the graph. This is something that you cannot change. You have your data, and the data comes with a certain resolution. There's no way you can change that. But what you can change is the bandwidth of the graph. So this is basically a user-chosen parameter, and it models how the graph is built. So the bandwidth is abbreviated by epsilon n, and it's the parameter that appears within the weight function. So we already saw that sort of in one of the first slides. You rescale your weight function for the graph with this parameter epsilon n, and you should think of this weight function eta as being non-increasing and having support in 0 and 1. And for this example here, you see that every point that is, all the points which are at most at distance epsilon will be connected by an edge. And if points are farther away than epsilon, they will not be connected by an edge. So this parameter really steers, well, the bandwidth of the graph and also the computational complexity. And as I already said, you want to choose this thing as small as possible, but it turns out you cannot choose it arbitrarily small. And indeed, there are quite severe restrictions of this length scale in terms of the resolution of the graph. And typically, so most methods that prove continuum limits, including convergence rates and so on and so forth, they need a restriction of this kind here, namely that the bandwidth is bounded from below by a fractional power of the graph resolution, and that this power is between 0 and 1. And this might look harmless, but if you sort of use such a bandwidth on real graphs, then you will see that the graphs are incredibly dense. So here here have just a very simple example, but you will have a lot of neighbors if you adhere to this condition. But then there are a few results which are valid for sparser graphs, where the bandwidth is only asymptotically bigger than the resolution, but not asymptotically bigger than a power of the resolution. And these assumptions are typically sufficient for gamma convergence. So for instance, the P-Laplacian result that I showed in the beginning by Lipschitz and Thorpe, this is valid given this lower bound here. But the question is, can you do even better? So can you work with the smallest bandwidth possible? And okay, so a partial step towards that question are our results from last year, which were published recently. Namely, we showed that for Lipschitz learning, namely for solving the infinity Laplacian equation, actually this bandwidth restriction is not only enough for giving you convergence, but you can even get quantitative rates of convergence. which is sort of completely new in this regime. But even more so, our recent results allowed us to reduce the bandwidth to the smallest bandwidth possible, namely where the bandwidth is proportional to the resolution of the graph. And you cannot choose a smaller bandwidth because as soon as the bandwidth is smaller than a constant times the resolution, your graph will not be connected anymore. It will just fall apart completely. So this is the smallest that you can get. And so far there have been no results at all for consistency of graph-based learning in that regime, with the only exception being a gamma-convergence result for the Dirichlet energy in 2 dimensions, which was published only very recently. And okay, this is the first step into the right direction. And then we have our results for Lipschitz learning, where we could even get convergence rate in that regime, which was pretty surprising for us. Okay, so these were the bandwidth restrictions. Let's speak very briefly about domain regularity. This is not such an interesting topic, but sort of the issue is that your domain comes with the geodesic distance, whereas your graph weights are typically computed with respect to an extrinsic distance, namely the Euclidean one, and this is not compatible. And if you want it to be compatible in the limit, you have to make some assumption, and this assumption is a compatibility condition of the Euclidean and the geodesic distance. And you basically have to be able to bound these 2 distances from above and from below with some error which goes to 0 sufficiently quick. And don't worry about this too much. It's satisfied for convex domains, for smooth domains, and even for certain non-convex domains, as we show. Okay, but let's now sort of look at the results for Lipschitz learning, so for the infinity Laplace equation. And what we could prove in our first work was the following. So you take a nice enough domain, you can take an arbitrary set of points to build your graph. So it doesn't have to be a stochastic sample, so it could be a grid, it could be anything. And then you get explicit convergence rates between the solution of the graph problem, which is this bold UN, and the solution of the continuum problem. And these rates look like that. And they involve some artificial parameter tau here. And you can then sort of optimize over tau to get explicit rates which only depend on the graph resolution delta and the graph bandwidth epsilon. And if you do that, sort of you get rates in 2 different regimes. So if the bandwidth is sort of reasonably small, which is interesting for us anyway, you get a rate which looks like this, and which just depends on how fast the bandwidth goes to 0 in comparison to the resolution of the graph. And it also depends on the domain regularity. And you can also write down a dense regime where the bandwidth is large, but this is not so relevant for us anyway. And then you also get a rate. But you see that sort of, you can always get a rate from this whenever epsilon n goes to 0 faster than delta n, because then this term will go to 0, this term will go to 0, this term will go to 0, and you can choose tau sufficiently, well, you can choose tau such that it also goes to 0, and then the whole thing goes to 0 and gives you a rate. So these were the insights from our first paper, and but they don't allow us to choose epsilon proportional to the bandwidth here, right? If you choose epsilon proportional to delta, you will just have a constant here. And in fact, this will even blow up if you send tau to 0. So these results don't work for, well, for the smallest length scales, but they are still sharp in the sense that they are valid for arbitrary sets of points, right? And if you take a grid, for instance, a regular grid, you cannot get a better term here than this arrow term. And so if you want to improve the arrow term, you have to get away from this arbitrary set of points. And what you can do is sort of what we did in our latest work. You can work on a stochastic graph instead. So here we assume that the graph omega n is a IID sample from a uniform distribution or a homogeneous Poisson point process. It doesn't matter. The result is the same for both settings. And then, in fact, you can also get convergence rates like this, where I don't use delta anymore. So the graph resolution is not present here anymore because it's a stochastic setting, and so you cannot control the graph resolution. but you can control sort of the asymptotic behavior of the graph resolution. And this is this log n over n to the 1 over d term here. So this is almost surely the resolution of your graph. And now it turns out that you can actually choose epsilon n to be equal to this quantity here, because then you will still get something which goes to 0, because you have a square root down here. So this is sort of the main improvement. In our results before, we didn't have a square root of epsilon here, but in these results, we have a square root of epsilon, which allows us to choose, well, epsilon equal to the resolution. And you can again optimize over this value of tau here, and you can choose the smallest length scale possible, and you get explicit rates, which even hold almost surely, and the rates are given like by that term. So it's basically the graph resolution to the power of 1 over 9. And let me remark here that these rates are probably very far from being optimal, just as the rates on the previous slides. But our proofs are extremely modular in the sense that if you exchange one of the statements, then you immediately get, or if you improve one of the statements, you immediately get better rates. And I will later get to the reasons why these rates cannot be optimal. Okay, let me speak very briefly about how you prove, or how we proved these convergence rates here. And for this, I would like to sort of tell you how you normally tackle continuum limits for graph PDEs or graph variational problems. And what's normally done is you have some discrete operator or some discrete functional which lives on your graph and comes with a length scale epsilon n. And then you show that sort of a solution to this problem gives rise to a solution of a non-local problem with the same length scale. And then you sort of send this length scale to 0 and you get some local problem like a PDE or a variational problem. However, the issue is that that this step here requires a lot of restrictions on the length scale epsilon n in comparison to the resolution of the graph, which we want to avoid. And therefore, we do not follow this approach, but we do something which we call meet me halfway, and it works as follows. So we also introduce a non-local operator, which is sort of situated here in the middle. And this non-local operator is basically, it looks like the graph infinity Laplacian. It just doesn't have weights. So the weights are equal to 0 or 1. And it has a length scale tau, which we think of as being much larger than the graph length scale epsilon. And then what we prove is basically we show that our discrete solution of a graph can be turned into an almost solution of this non-local operator with this much larger length scale. And then we come from the other side as well. We show that our continuum problem that we want to converge to also gives rise to a solution of this problem here in the middle. And then we can compare the two solutions that we have from the right and from the left. We can compare them here in the middle. And in particular, all of the restrictions that you typically have on the length scale epsilon, they now apply to the length scale tau, which can be much larger. So we're fine with having a lot of restrictions on tau. But then this still allows us to choose epsilon small, and tau will just affect the rate, but not the question whether the problems converge or not. And so for proving or for following this proof strategy, it turns out that it's very important to understand the distance function on the graph. And the reason is that the solutions of our discrete problem, but also the solutions of our continuum problem, they both can be characterized in terms of the comparison with Cohn's principle, which basically states that U is a solution of the continuum problem, but also of the graph problem, if and only if you have a comparison principle of that form, where here you have the distance function in the continuum, and there's also a graph version where you have the graph distance. And so the idea is that if you can prove that the graph distances converge to the continuum distance with some rate, then we can use this comparison with Cohn's principle to carry over the convergence rate. And this indeed works. And I will not go into details now how this comparison with Cohn's principle is applied. I would just like to speak a little bit about the convergence of the graph distance functions. So which is sort of the essential ingredient. So I will skip over a few things here, and I will only go sort of speak about the convergence of the graph distance, because what it will what turns out to happen is that our convergence rates that I presented you in the beginning, they will involve a term which looks like this. So this is we call it a ratio term R, and it basically features the quotient of two different graph distance functions. The first one is basically the graph distance from a point X to a point Y, which has distance tau, so it lies in a ball around X. And down here you have the graph distance from X to a point Y, which has distance 2 tau. So you would kind of expect that the quotient of these two graph distances is close to 1/2. And then you subtract 1/2, so you should expect that this ratio term here is very small. And indeed, our ultimate convergence rate just depends on the convergence rate for this ratio. And so let me now show you how you can estimate this ratio in an easy way and also in a more sophisticated way. Okay, let's start with the easy way. And the easy way is if we allow our bandwidth to be strictly larger than the resolution. And remember that the distance function on a graph was defined like this. So we basically sum up all the reciprocal weights for a path in the graph, and this gives us our distance function. And indeed, it's pretty easy to prove that this graph distance function can be bounded from above and from below by the geodesic distance on your domain, or the Euclidean distance, if you wish. So the bound from below is very trivial to show. It's basically just a triangle inequality. And for the bound from above, what you do is the following. You take a path which realizes your continuum distance, and you discretize this path to the graph, which you can do because your graph is sufficiently dense. And then this discretization gives you sort of this arrow term here, and also this arrow term back here. But sort of the message is that your graph distance is sandwiched between the Euclidean distance and the Euclidean distance, and these arrow terms go to 0 if the graph resolution goes to 0 and if the bandwidth goes to 0 faster. And so since we have this sandwich thing, it's now very easy to, okay, let me skip over this. It's now very easy to estimate this ratio here, because you can upper bound the graph distance here, you can lower bound the graph distance here by more or less the same expressions up to some errors. And then you get a rate for this ratio, which looks like this. And this is precisely the rate that we saw in the first theorem. So the rate of the Lipschitz learning problem only comes from the rate for this ratio convergence of distance functions. And now, of course, we can try to improve this ratio convergence for distance functions by moving away from arbitrary graphs and moving towards random graphs. All right, and so this is sort of the last thing that I want to speak about in this talk. And for this, let us simplify the setting a little bit. Let's assume omega is convex, so we don't have to worry about these geodesic distances anymore. And let's assume that our weight function on the graph is sort of the natural weight, namely it's 1 over the distance for every point which is sort of closer than epsilon to another point. And for this choice of weight function, the graph distance has a much easier form. Namely, it's just the sum over the Euclidean distances between points in your graph path. Okay, and of course we can still use the previous estimate and that I showed you, which simplifies drastically in this setting. You get this estimate here. However, if you now choose epsilon proportional to delta, this upper term will not converge to the same thing as the left term. It will converge to a constant times the Euclidean distance. And this only gives you boundedness of the graph distance, but it doesn't give you convergence. So you sort of have to change your method here a little bit. And as it will turn out, and as I will show you sort of in the last minutes of the talk, is that if your graph is a Poisson point process or an IID sample, it doesn't matter, then indeed there exists some number sigma, which is bigger than 1 and depends on the dimension, such that the graph distance converges to sigma times the Euclidean distance. So this is some sort of homogenization effect. You don't converge to the Euclidean distance anymore, but you converge to a multiple of the Euclidean distance, and the multiple itself is unknown. But it also doesn't matter for us because we're just interested in the ratio of two distance functions. So then this constant will just cancel out. And so now let me use the last minutes to show you how in this stochastic setup you can get this convergence to a multiple of the distance function. And okay, so this is a very brief recap on Poisson point processes. I might just skip over that. You can just think of a Poisson process as the same thing as an IID process, but you don't know how many points you have. You just know that in expectation you have n many points. So that's the Poisson process. But Poisson processes have very important properties. Namely, you can shift them around, you can rotate them, you can restrict them, and you can dilate them, and they always remain a Poisson process. It's just that the intensity changes. So, and the intensity is basically the expected value of points in that process. And because of this sort of invariance, it suffices to study the distance function from 0 to a point on the x-axis, because it's just, I mean, you can just rotate things around. And you can also just work on a unit intensity process. That means that in a box of volume 1, you expect to have precisely 1 point. And okay, then you can set up a distance function, which is nothing but the graph distance function from 0 to this point on the x-axis. And the graph in this case is the Poisson process. And you have step sizes hs here, which now have to grow to infinity because we're working in this rescale setting. So instead of taking more and more points, we fix the number of points and we just take larger and larger distances. So we send s to infinity instead of sending n to infinity as in the previous approach, but this is perfectly equivalent. And so the illustration of what you should have in mind is this. You start at a point 0 and you go to this point on the x-axis, which is s times the first unit vector, and you send s to infinity, and you want to understand how linear these distances become if s becomes very large. And so then you have to use completely different techniques. And what you can do is you can use sub-additive theory. Because the triangle inequality that you always have for graph distances immediately implies that this graph distance from 0 to s is a sub-additive function in expectation. So it satisfies this property here. And this would immediately give you that, the graph distances are asymptotically linear. So if you divide them by s, they will converge to some constant. However, all of that does not work in our case, because the expected value of these graph distances are infinity, because it could always happen that because of the stochasticity of the graph, you have some void regions, and so then the graph is not connected and you have infinite distances. So this can always happen. And so what you do in fact is you regularize the distance function by adding a few points to our random graph such that it becomes a connected graph. And then you get this distance function Ts prime, which, however, coincides with Ts with very high probability. And you can do the same program for Ts prime. You can show that it's asymptotically linear using some sub-additive ergodic theory. And if you rescale everything to the original problem that we're interested in, this gives us that the graph distance function on our graph with n vertices, so we rescale back, converges as n goes to infinity to a multiple of the Euclidean distance, as I mentioned previously. Another question is, how do you get convergence rates for this convergence? And here you have to use other stochastic tools, namely concentration of measure and super additivity of this distance function. And then you can also get explicit rates. Let me not go in detail for the sake of time here. Let me just show you the original, the final result. Okay, this on the next slide. So the final result that we get is that this ratio that determines our rate for the Lipschitz learning problem, this ratio -1/2, has an error which looks like that. It has a couple of log factors, but you divide it by the square root of s. And so if s goes to infinity, this converges to 0 and you have an explicit rate. And this arrow here is completely determined by the random fluctuations of the distance function divided by s. And so this is what I meant when I said that our rates or our proofs are very modular, because characterizing these random fluctuations is a sort of a very big topic in the stochastics community. And if you can improve these random fluctuations from what we got, then you immediately get better rates for the conversions of the distance functions. Okay, let me show you some numerics to conclude. So the first illustration here is that you can take an infinity harmonic function on a funny domain, namely this star-shaped domain. And if you send a number of graph vertices to infinity, you can sort of, with the eyeball matrix, see that this nicely converges. And you can also look at convergence plots for two different weights. So here the graph weights are just constant, either 0 or 1. And here the graph weights are singular, that means 1 over the distance. And you get rates which are, well, sublinear in this situation, and even superlinear here. So they are much better than delta to the 1 over 9, which is what we got from our theory. We can also look at sort of these percolation length scales in a bit more detail. And what we see here on the left is how for different sizes of your step sizes, your distance functions converge to this constant multiple times the distance function. And sort of here we basically plot the value of this constant, which is strictly bigger than 1 in this percolation setup, whereas for larger length scales, it would be equal to 1. And also for this ratio conversions, which was the ultimate thing that we are interested in, you see that these ratios nicely converge to 1 over 2, which is what we need. And the rates, which are plotted here on the right, they even look linear, whereas our theory gave us 1 over square root of s. So this would be a slope of 1 over 2, but here you get a slope of 1. So also here the rates are better, but the reason is this stochastic fluctuations issue, as I told you. So let me just come to the outlook. So what we saw today is that continuum limits for Lipschitz learning, or the infinity Laplace equation on the graph, they require only minimal assumptions on the graph itself, and they even give you convergence rates. And the main ingredient for the rates are the convergence rates for the distance functions itself. So it suffices to study this first order problem in order to get convergence rates of this second order problem up here, if you wish. And in the second, or in the last part of the talk, which is very brief, of course, I even sort of hinted at that you can get convergence rates for percolation length scales. And this seems to be the only result in graph-based learning where you can actually get convergence and convergence rates for such small length scales. And future work would include improving these random fluctuations of distance functions on Poisson clouds from order square root of s to logarithmic, which would then significantly improve the rates. But this seems to be a major open problem in this community, as well as the proof of a strong form of superadditivity, which I didn't speak about today. And of course, it would be interesting to extend this approach to other semi-supervised learning methods on graphs, like standard Laplacian learning, which is the linear problem. And these recent results by Breides and Cariocci for gamma convergence of the Dirichlet energies in 2D might be a first step in that direction. And finally, so you can also use the insights that we had to prove statements from PDEs. So this has nothing to do with learning, but you can actually prove convergence rates of the P Laplace equation to the infinity Laplace equation as P goes to infinity, following a very similar proof strategy. And yeah, so this talk is based on these two papers, which I spoke about in the beginning. And yeah, with this, I would like to conclude the talk and